In Module 6, Lesson 7, we'll continue looking at the mean as a balance point. In Lesson 3, Robert gave us an informal interpretation of the center of a data set. In Lesson 6, Michelle developed a more formal interpretation of the center as a fair share mean, a value that every person in the data set would have if they all had the same value. In this lesson, Sabina will show us how to interpret the mean as a balance point. Sabina wants to know how long it takes students to get to school. She asked two students how long it takes them to get to school. It takes one student 1 minute and the other student 11 minutes. Sabina represents these data on a ruler, putting a penny at 1 and another at 11, and shows that the ruler balances on the eraser end of a pencil at 6. Note that the mean of 1 and 11 is also 6. Sabina thinks that there might be a connection between the mean of two data points and where they balance on a ruler. She thinks the mean may be the balancing point. What do you think? Will Sabina's ruler balance at 6? Is the mean of 1 and 11 equal to 6? Sabina shows the result on a dot plot. Sabina decides to move the penny at 1 to 4 and the other penny from 11 to 8 on the ruler, noting that the movement for the two pennies is the same distance but in opposite directions. She notices that the ruler still balances at 6. Sabina decides that if data points move the same distance but in opposite directions, the balancing point on the ruler does not change. Does this make sense? Notice that this implies that the mean of the time to get to school for two students who take 4 minutes and 8 minutes to get to school is also 6 minutes. Sabina continues by moving the penny at 4 to 6. To keep the ruler balanced at 6, how far should Sabina move the penny at 8, and in what direction? Since the penny at 4 moved 2 to the right, to maintain the balance, the penny at 8 needs to move 2 to the left. Both pennies are now at 6, and the ruler clearly balances there. Note that the mean of these two values, 6 minutes and 6 minutes, is still 6 minutes. Now it's your turn to try balancing two pennies on a ruler. Tape one penny at 2.5 on your ruler, and then follow the directions through exercises 1 and 2. In example 2, we're going to investigate deviations to understand those. In the above example using two pennies, it appears that the balance point of the ruler occurs at the mean location of the two pennies. We computed the distance from the balance point to each penny location and treated the distances as positive numbers. In statistics, we calculate a difference by subtracting the mean from the data point and call it the deviation of a data point from the mean. So points to the left of the mean are less than the mean and have a negative deviation, and points to the right of the mean are greater than the mean and have a positive deviation. Let's look at Sabina's initial placement of pennies at 1 and 11, with a mean at 6 on the graph below. Notice that the deviations are +5 and -5. What is the sum of the deviations? So if we add +5 and -5, we should get 0. Similarly, when Sabina moved the pennies to 4 and 8, the deviation of 4 from 6 is 4 minus 6, which is -2. And the deviation from 8 to 6 is 8 minus 6, or positive 2. And here again, the sum of the two deviations is 0, since negative 2 plus positive 2 equals 0. It appears that for two data points, the mean is the point when the sum of its deviations is equal to 0. Referring back to exercise 2, where 1 penny was located at 2.5 and the mean was at 6. We'll answer these questions based on exercise 2. So when 1 penny was located at 2.5, the other penny was located at 9.5. Calculating the deviations of those two pennies, keeping in mind that the mean was at 6, we would do 2.5 minus 6, which is negative 3.5, and 9.5 minus 6, which is 3.5, positive. And the sum of those two deviations then, negative 3.5 plus 3.5, is 0, which proves that 6 is the mean. Sabina wants to know what happens if there are more than two data points. Suppose there are 3 students. One student lives 2 minutes from school, and another student lives 9 minutes from school. If the mean time for all 3 students is 6 minutes, she wonders how long it takes the third student to get to school. She tapes pennies at 2 and 9, and by experimenting finds the ruler balances with the third penny placed at 7. To check what she found, she calculates deviations. The data point at 2 has a deviation of negative 4 from the mean, if our mean is 6. The data point at 7 has a deviation of positive 1 from the mean. And the data point at 9 has a deviation of positive 3 from the mean. So the sum of the 3 deviations is 0, since negative 4 plus 1 plus 3 equals 0. So the mean is indeed 6 minutes. Robert says that he found out that the third penny needs to be at 7 without using his ruler. He put 2 and 9 on a dot plot. He says that the sum of the two deviations for the points at 2 and 9 is negative 1, since negative 4 plus 3 equals negative 1. Remember, those are the deviations from our mean of 6. So he claims that the third data point would require a deviation of plus 1 to make the sum of all 3 deviations equal to 0. That makes the third data point 1 minute above the mean of 6 minutes, which is 7 minutes. Imagine you are balancing pennies on a ruler. Suppose you place 1 penny each at 3, 7, and 8 on your ruler. Sketch a picture of the ruler and then decide at what value you think the ruler will balance, and mark the balancing point with a symbol that is a triangle. So looking at our sketch, we have 1 ruler at 3, or 1 penny at 3, 1 at 7, and 1 at 8. The balancing point we've marked with the triangle, and we're saying that the balancing point is 6. What is the mean of 3, 7, and 8? And does your ruler balance at the mean? So if we look at that, The deviation of 3 from 6 is negative 3. And then the deviation of 7 from 6 is positive 1. And the deviation of 8 from 6 is positive 2. If we add negative 3 plus 1 plus 2, we get 0. So it does balance at that point. Now if we show part A on a dot plot, we can also mark the balancing point with the same symbol. And we can see the same as we did on the ruler. A penny on 3, 1 on 7, 1 on 8, and our balancing point at 6. What are the deviations from each of the data points to the balancing point and the sum of the deviations? Well, we did that in part B. And so the value of the mean is 6. Now suppose you place a penny each at 7 and 9 on your ruler. If we then estimate where the third penny would need to be on the ruler so that the ruler balances at 6, and mark that point on the dot plot, we would find that that value has to be at 2. And we mark the balancing point with our triangle symbol. Explain why your answer in part B is true by calculating the deviations of the points from 6. So we'll start with our third point, which is 2 minus 6 equals negative 4. That's our deviation of the first point. Then 7 minus 6 equals 1. That's our deviation from our second point. And our third point, which is 9 minus 6, equals 3. Then we take those three deviations, negative 4 plus 1 plus 3 equals 0, proving that our mean is actually 6. Suppose you place 2 pennies at 7 and 1 penny at 9 on your ruler. Then we estimated where to put the fourth penny so that the ruler balances at 6, and mark the point on the dot plot above. We did that. We marked our balancing point 6 with the triangle symbol. And now in part C, we will prove that the answer in part B, which was 1, is true by calculating the deviations. So 1 minus 6 equals negative 5. 7 minus 6 equals positive 1. And again, there's a second point there. 7 minus 6 equals 1. And finally, a point at 9. Whoops. And 9 minus 6 equals 3. And taking all of our deviations, negative 5 plus 1 plus 1 plus 3 does equal 0, proving that our mean is 6. Not all data distributions on a ruler are going to have a fair share mean or balance point of 6, however. What if the data were 1, 3, and 8? Will your ruler balance at 6? Well, there's our deviations. 1 has a deviation of negative 5, 3 has a deviation of negative 3, and 8 has a deviation of positive 2. When we add those three numbers together, we're going to get negative 6. So it won't balance at 6. Let's see if the balance point is at 5. The deviation of 1 from 5 is negative 4. Deviation of 3 from 5 is negative 2. And the deviation of 8 from 5 is positive 3. The sum of the three deviations is negative 3, since negative 4 plus negative 2 plus 3 equals negative 3. That's closer to 0 than before, so let's keep going and try 4 as the balance point. The deviation of 1 from 4 is negative 3. The deviation of 3 from 4 is negative 1. The deviation of 8 from 4 is positive 4. And the sum of the deviations is 0, since negative 3 plus negative 1 plus 4 equals 0. The balancing point of the data distribution of 1, 3, and 8, shown on your ruler or on a dot plot, is at 4. The mean of 1, 3, and 8 is 4. Recall in Lesson 6 that Michelle asked 10 of her classmates for the number of hours they usually sleep when there is school the next day. Their responses in hours were again this data list. It's hard to balance 10 pennies. Instead of actually using pennies and a ruler, draw a dot plot that represents the data set. And here's our dot plot. If we use the dot plot to find if we use our dot plot to find the balance point, we would want to find the deviations of the data points from our fair share mean of 9 hours. So 7 minus 9 equals negative 2. 8 minus 9 equals negative 1. And again, 8 minus 9 equals negative 1. And again, 8 minus 9 equals negative 1. And one more time, because there are 4 8s. 8 minus 9 equals negative 1. Then we have a 9. 9 minus 9 equals 0. We have two 10s. 10 minus 9 equals 1. 10 minus 9 equals 1. And two 11s. 11 minus 9 equals 2. And 11 minus 9 equals 2. Finally, we'll have to add those deviations to see if they equal 0. Negative 2 plus negative 1 plus negative 1 plus negative 1 plus negative 1 plus 0 plus 1 plus 1 plus 2 plus 2. And that does equal 0. So our fair share mean would be 9 hours. In this lesson, the balance process was developed to provide another way in which the mean characterizes the center of a distribution. The mean is the balance point of the data set when the data are shown as dots on a dot plot or pennies on a ruler. The difference formed by subtracting the mean from the data point is called its deviation. The mean can be defined as the value that makes the sum of all deviations in a distribution equal to 0. The mean is the point that balances the sum of the positive deviations with the sum of the negative deviations.